Hi everyone, this is my Physics 2211 Lab 2 report video. Here is an overview of what I'll be covering in this video. I'll start off with the introduction, then I'll move on to the fundamental principles, along with procedures and experiment, analysis from the tracker, sources of error, and I will conclude with the discussion questions. The main purpose of this lab was to observe an object that was thrown, moving like a projectile, and using tracker to extract the object's motion and comparing it with a computational model based on the momentum principle. In this experiment, the object that I used was a wadded up ball of paper. Tracker was used to analyze the video, along with GlowScript, which was used to construct the computational models. A preview of my results is that my observed model appeared below or lower than the computational models on GlowScript in the combined graph on Excel. Moving on to fundamental principles, we used a computational model based on the momentum principle because it states that the net external force acting on a system causes a change in its momentum over time such that the net force is equal to delta P over delta T. This is a brief refresher on what we talked about in the last lab report. So as you can see here, we have the velocity update formula and the position update formula, and these allow us to track the motion of the projectile computationally, and they were also derived from the momentum principle, which we talked about in the previous slide. Starting off with gravitational force, the force of gravity is equal to 0, negative mg, 0, where g is equal to 9.8 meters per second squared. We also have drag force, which acts opposite to the object's motion, given by F drag is equal to negative b times v squared times v hat. For this lab, we threw a wadded up ball of paper across a table in a projectile-like motion, using a ruler as a calibration stick. We then uploaded the video to Tracker to track the motion of the ball in each frame. We then created a computational model using the starter code on GlowScript to get the predicted trajectory of the object. We collected data from both Tracker and GlowScript to create spreadsheets, and we compared and contrasted the observed and predicted data points from each to create a graph on Excel. So the system here is the wadded up ball of paper, and the surroundings include the table surface, the earth, gravity, air resistance, etc. So moving on to the analysis from Tracker, the initial position is 0.419, negative 0.5920 meters. And circled in red are the data points that I used to calculate the initial velocity, which can be seen here. So highlighted in orange is the code that I edited for the computational model without drag. So the mass of the wadded paper is 0.004. The initial conditions were set from Tracker data points from the previous slide, and delta T was set to 0.033, which is the size of each time step on Tracker. The net force is 0 negative ball dot m times g, 0. And again, highlighted in orange is the code that I edited, but this is for the computational model with drag. So the mass, initial position, initial velocity, delta T are all the same. I changed B to be 0.001 and the net force to be F gravity plus F drag. Here are some screenshots of output from running the programs without drag and with drag. So this is the graph that was created that shows the observed trajectory of the object versus the predicted observed trajectory. The Tracker model, which is shown in green, is lower or below the predicted models, which might indicate that gravity and drag are acting on the paper ball. The orange highlights our gravity and drag model, and the blue is our gravity model. So some possible sources of error include tracking errors, such as misidentifying the exact point on the wadded up paper ball. Another possible source could be timing issues, such as video lag on Tracker, which might cause delays. And lastly, we have errors in calculations, and this could be from code inaccuracies or miscalculations in initial velocity. Concluding with the discussion questions, what does it mean? So the answer to this question is that the top figure, the model without drag, does not predict terminal velocity. However, the bottom figure, the model with drag, does slightly indicate terminal velocity, and you can see a slight curve that is beginning to flatten out, although this might not be indicative of terminal velocity. Now moving on to what if. So the answer to this question is that the object would take longer to reach the ground because when the paper ball is thrown straight up, it has to travel upward against gravity, slow down, stop, and then fall back down past the point that it was released before reaching the ground. And this can be given by the following. Delta t is equal to 2 times the initial velocity in the y over g. Thank you for watching this video.